Okay, so we talked about those guys. So ethers, we know that it's gonna be in the second exam. He didn't talk about them at all. And then what was okay, oxidations and reductions, that's gonna be in both exams. Oxidations is just gonna be on the second exam. And then of course that's reduction, so that's in the exam. Okay, originally I had put my cat in here for protecting groups, but apparently that's gonna be for this exam, according to what I saw in the extra credit quiz. So yes, it's just like the first part though. I didn't see any questions on tosylate or mesylate, but just in case I'm gonna cover them both. So I'm gonna go a little bit fast this session so we can cover like all of the concepts. And then for Monday, I prepared a little review. It's not a review like you guys are used to, but it's basically a 6-page document in where I put like all of the main things that you should remember and shortcuts that you should remember. So we're gonna go through those on Monday. It's like a summary, yes, like a condensed summary for you guys to know. I'm gonna be posting it as well during the weekend so you have access to it while you study. And on Monday, we're just gonna talk about that and we're gonna do some examples on what I mean by certain things that I put in there. And if you have any specific questions, like you guys can just give me some problems and we can do them on the board. Yes. It seems like it, yes. But yeah, with Dr. West, it's like a 50-50 shot. Like sometimes he likes to focus more on conceptual stuff, sometimes more on application. Lately, the trend has been mostly on conceptual stuff, but again, like it varies semester by semester. Okay. So we finished last session just talking about Grignards, right? We talked about the conceptual stuff. We went over one of the mechanisms, and then we were about to start the second one. But before we left, I gave you guys a little shortcut in here, right? So let's quickly review Grignards. So first of all, remember, Grignards is going to be both a strong nucleophile and a strong base. So that means that whenever you have anything acidic like carboxylic acid, you're not going to do a reduction. It's just going to be an acid-base reaction. So remember, be careful with Grignards. You have to look at everything in the molecule to see what you're going to do. And then really quickly, how do we know we're doing a reduction? Exactly. If we lose the amount of bonds between carbon and oxygen, we're doing a reduction. And then since exam is approaching, let's review a little bit of chapter 9. What's going to be the major contributor for the N+1 peak? Carbon. What about the N+2 peak? Major contributor. Bromine and chlorine. What's the major one? Bromine. Perfect. What happens if I have an odd number as my N+ peak? What about nitrogen? Odd number of nitrogens, exactly. How do I know I'm doing complex multiplicity? How do I know that I'm gonna do complex multiplicity? If the coupling is different or if we see that word theoretically. Okay, are we gonna group together the hydrogens in a benzene group? They're just gonna be in one signal unless, exactly. So remember, always read the entire question because he puts that reference at the very end, okay? And then what else? I think that's pretty much it. What are the two scenarios for diisotopic hydrogens? What about the double bonds? How do you know they're diisotopic? If you create cis and trans isomers, exactly. And what about the chiral centers one? What's the scenario for that one?
Chiral center and you're creating second chiral center with the
Exactly, yes. You have an established chiral center and you're forming a possible chiral center. And then for this chapter, I'm sorry? For the isotopic. And then for this chapter, we were talking about addition reactions. There we go. Okay. What are the rules for hydroboration oxidation? That's more, sorry, anti-Markovnikov's rule. And then what about the stereoselectivity? It's in. Exactly, it's in. Then what's the only reaction in where we can do the rearrangements? What's the reaction in where we can do the rearrangements? Acid catalyzed hydration, beautiful. And then one more. What's the mechanism that I'm gonna follow if I use POCl3? POCl3. It was like the one special case that we talked about after addition reactions.
Create OH on,
It's always gonna follow an E2 mechanism, exactly. That was a dehydration example. Okay, so now that we reviewed a little bit of everything, let's keep going with a handout. Yes. Yes, they're always posted. You guys have access to them. Like I sent an announcement and you should just check out the link there. It's a YouTube channel, so you guys can check it out. So yeah, you have like most of the sessions, I think. I think we missed like the first 3 sessions, but yeah. And then we also missed the one where we didn't have Wi-Fi, so. Okay, let's get with those. Okay, so pretty much it's the same mechanism that we did with the sodium and lithium reagent, right? The only difference is that this time I'm adding a carbon chain instead of just a hydrogen. Now, if we have an ester, for example, let me erase this so we can see this clearly. If we have an ester, for example, we have to keep in mind that we have a leaving group. So it's not going to be as simple like we saw it with the ketones and aldehydes. Okay, so what's going to be the very first step? The dipole moment, exactly. So yeah, we have a delta negative, delta positive. And then what? This carbon, yes. This carbon is the electrophile. Beautiful. What else? Which is? Because remember that MGBR is just going to go away, and the actual nucleophilic species is going to be that carbon chain. Yes. Yes. So yeah, for greens, you don't have to worry about magnesium and bromine. Okay, so once we have the nucleophile, where am I going to tag it? I attack that electrophilic carbon, and then to not break the octet, electrons go up towards the oxygen. So far I'm forming a little intermediate. I have O minus, and I have an ethyl change. What's going to be the next step? What's going to happen? How? The hydrogen?
The electrons will get used.
Exactly. This is the point where we reform the double bond. So electrons in that oxygen with a negative charge go back down, and that's how we kick out that leaving group. So that means that now we have a little ketone plus our leaving group. And we have a negative charge in here. Okay, so I have that. What am I going to do now? Is that going to be my final product, a ketone with a alkoxide? What am I going to do? The green reagent is going to come again, and it's going to do the attack. So that ethyl group is going to be attacking my new electrophilic carbon. And again, I kick up the electrons towards the oxygen. Oops. Okay. So after that, I'm going to be creating, what's going on? Okay, that intermediate that now has that first ethyl group from the first attack and that second ethyl group from the second attack. And we still have that byproduct. Very last step, what's going to happen? H2O is going to protonate them, exactly. So simple acid-base reaction. And then we end up with 2 alcohol groups. We have those guys. Okay, so what kind of alcohols did I just create? Primary, secondary? tertiary,
with
and tertiary, exactly. So that's the main part of Grignards, because we're adding that R group, we're able to create tertiary tertiary alcohol groups. Okay, so for questions on that reaction with the ester. Pretty simple. It's pretty much the same mechanism. Again, the only difference is the nucleophilic species. With sodium and the lithium reagent, we use the hydride ion. For Grignards, that carbon chain. So far, questions on the reaction? We're good so far? Okay. Let's see. Okay, before we continue with the rest of the reactions in here, let's quickly do a practice problem over here. Okay, so just take a look at that reaction. What do we think the product is going to be?
You open up the ring with the ester. And then you just end up with a methyl entering the chain instead.
Okay, so what would be the final product?
Final.
What kind of degree of alcohol are you talking about?
They're going to be creating a secondary alcohol.
Okay, we say a secondary alcohol. Do we all agree? We're going to end up with an alcohol group?
We're going to end with two alcohols first.
We're going to end up with a tertiary alcohol, primary alcohol, tertiary. In this case, we're not going to assume that we have two equivalents.
The degree is how many other R groups are connected to the OH, right?
How many R groups are connected to the carbon that has the OH group?
Okay.
Okay, so we pretty much think that we're going to end up with an alcohol group. Now, remember, secondary alcohol. Okay, so we're either between secondary or tertiary, right?
I have a question though. It is gonna the ester part. The other double bonds don't interact with benzene, right? But it will interact with that ester, and it's gonna open up, right?
Okay, so first of all, let's go back to the basics. Grignards is both a good nucleophile and a strong base. And I told you that we're not going to do a reduction whenever we have any acidic protons. And that's why I always told you, look at the entire molecule. In this case, we have a phenyl group. That alcohol is going to be considered relatively acidic. So instead of breaking up the cyclic ester, we're just going to do a simple acid-base reaction. So we're just going to end up with an alkoxide. So we're going to be, we're going to be preserving that cyclic ester over here. And then we still have that benzene group. But now we have the deprotonated version of that alcohol. Okay, because that's what's going to happen first. If I have excess of the Grignards, then potentially I could do the reduction. But in this case, because we're just given that reagent plain and simple, we don't have any equivalents or anything, nothing says that we have excess. So you're just going to do that acid-base reaction. Okay, that's the order for Grignards. If you have anything acidic, acid-base reaction. If everything is neutral, that's when you can proceed with the reduction. So far, questions on that?
So in this case, would the methyl group be attached to that oxygen?
Which methyl group? The
Grignards.
whoops. In this case, that methyl group. Let me show you. So this is a nucleophile slash base. Technically, your byproduct is going to be a methane because it's just going to get that extra hydrogen, and that's it. So again, please be careful with Grignards. It can be a tricky reaction. You have to look at the entire molecule, yes. We don't assume excess. We're only going to assume excess with lithium.
Because the methyl group attack.
Okay. Let's keep talking about a conceptual question in here. Okay, so in this case,
Is the magnesium bromide a free floating product?
yeah, it's just going to be floating around. It's not going to be the main thing that we're focusing on in this case.
Can you remind that happens to the graveyard, like the magnesium bromide,
Magnesium bromide just goes away. It's gonna be floating around the solution, and then we're left with our carbon chain. That's gonna be a nucleophile. Exactly. Okay, so let's keep talking about conceptual questions. So out of those 4 molecules, which one is not gonna be able to form a Grignard reagent?
The
Carboxylic acid.
graduation.
Do we all agree?
Yeah.
Yes, beautiful. Simple as that. As soon as you see something acidic, an alcohol group, this guy is not gonna work for Grignards. Okay, so do we see the pattern now of why we're not gonna do a Grignard reaction like as a reduction? Do we see it now? Feeling better? A little confused? Oh, okay, that makes more sense. Question? Because the alcohol is gonna be considered acidic. Remember at the very beginning of the handout, we talked about alcohols. Are they gonna be acids or bases? And we said that they were gonna be acids. So that's where that comes into play in this case. In this case, I'm just showing alcohols because that's the most common group that you're gonna see that's acidic for Grignards. It usually doesn't use any other molecules, but again, the concept is that if you see anything acidic, you're not gonna do a reduction. You're doing an acid-base reaction, and that's it. Yes.
Well, those are the apples, magnesium bromide, but that's it.
At this one?
Yes. The last step, where protonates the oxygen to create.
We're just
You
protonating.
get a free floating oxygen. That the H2O, what happens?
It's,
It loses hydrogen, then you just got a free floating oxygen.
I mean, technically, yes, but remember, solvents are gonna be like in excess because it's basically the liquid around the reagents.
And then the oxygen bonds with another oxygen.
yeah.
to create oxygen.
Exactly, so they're gonna be happy. They're gonna be okay. Okay, okay, so we still have time. Okay, let's do this next problem. This time with a cyclic ester. Okay. So very first step, what's gonna happen?
pH is a friend.
So first of all, magnesium goes away, and that phenyl group, that's what the pH means, a phenyl group. So that's just a benzene group. Yeah, just a ring. Now, once we have that, now we attack that electrophilic carbon. So we create our little intermediate, which is gonna be this guy. Really? Okay. Then we have an O minus, and we're adding that phenyl group. Okay, in this case, I'm just gonna write pH, but technically the actual structure, it's gonna be a full benzene ring. So just so you guys know, that's what it means, a benzene group. Okay, what's gonna happen now?
Yolk is protonated.
I'm gonna protonate this oxygen?
Oh no, it breaks off the other O, correct?
How?
The
Creates double bond.
Exactly, the electrons are gonna go back down, reform the double bond, and that's how I kick open that carbon chain, hold that cyclic structure. Now let's see, after this, we're gonna end up with pH. And 5. Three, 4, and 5, and carbon 5 is the one with the oxygen minus. Okay, after that, I have a ketone and an alkoxide. What's gonna happen?
pH is gonna attack from the water.
Okay, and that's gonna give you my final product. What's gonna happen?
Oh, it keeps going, it breaks that double bond from the O, right?
Mm-hmm. So that means that the Grignard reagent is gonna come again. So that phenyl group is gonna attack that carbon. And again, I kick up the electrons towards the oxygen. So I have that phenyl group from the first attack, the one from the second attack. Sorry. I'm not gonna kick out anything in this case. I don't have any leaving groups. It's just carbon chains. So I have that O minus again. From the second attack, because remember, we have an ester. From esters, we have to do a double attack with the Grignard reagent. So that's why we have two phenyl groups at this point.
That there's multiple, like, they're all.
Mm-hmm. For esters, yes, unless, again, remember, unless you see something acidic, you're not gonna see that excess because he's trying to test you on that concept, okay? So if you see anything acidic, reductions are not gonna happen. Only the acid-base reaction. Okay, at this point, what's gonna happen?
It attacks the
Mm-hmm.
water.
Water is just gonna come and protonate it. So now we end up with our alcohols. And what kind of alcohols did we just create? What are the degrees?
Primary and tertiary.
Primary and tertiary, exactly. Okay, so far, questions on that one?
What's the like point of the second tag? Wouldn't you require two equivalents?
Technically, you're supposed to assume that you have excess whenever we're trying to reduce any esters, like what we saw with the lithium reagent, remember? We just assumed that we had excess of that reducing species. Because again, reductions, we're trying to get rid of all of those
Those
bonds.
two
Mm-hmm. Yes.
So if this, instead of it, it just opens it.
Mm-hmm.
That's like it.
Exactly. Yes. Beautiful, exactly. Yes. On this part? Okay. Now again, I'm just showing you the mechanism so everyone can follow where exactly I'm gonna add that Grignard reagent. And for the previous reaction, it was for the hydrogens because it's gonna give you isotopes sometimes. And then again, once you feel more comfortable, that's when you can just move on to using the shortcuts that I gave you. So let's quickly take a look at them, which were over here. So let's do the one that we just did actually, the one with the ester over here. So again, you have some sort of Grignard reagent, that's just a carbon chain, and we have some sort of solvent. At the very end, I know that this is gonna act as my leaving group, so I'm gonna have two products. At the end, they're both gonna be protonated with the solvent. That's what that hydrogen is green. It came from the solvent. And then, because we know that we do a double attack on Grignards, sorry, on esters, that's why I'm gonna add the Grignard reagent twice into that alcohol group, sorry, into that carbon. So it's basically just a pattern to memorize. But again, knowing the mechanism can help you a lot in case you get confused with the shortcut. Okay, so far questions. We're good? Yes. Sorry? Grignards, yeah.
So for the first example, I'm sorry, I need to understand for the ethyl bromide one, all the way up.
Oh,
So there would be two equivalents of the methanol, essentially, as a byproduct, because you're doing the reaction twice, so there's two equivalents of the methanol.
yes.
That's how it goes.
Okay, so and again, let's quickly go back to the shortcut for the other reactions. Remember, ketones and aldehydes are very reactive. So they're gonna work with either the sodium or lithium reagent. Most of the time, you're just gonna see it with the sodium reagent. The difference is that this time, instead of adding that carbon chain from the Grignards, we're just adding one hydrogen that came from that reducing species. And again, remember, the nucleophilic species from those reactions is that hydride ion. So that hydrogen with a lone pair and a negative charge. Very important for you to know that. And then same process with our esters. And in this case, because we're not talking about Grignards, we can also reduce carboxylic acids. So that's the main difference between the lithium reagent and the Grignards reagent. And again, because we have leaving groups, we're repeating the attack twice. So that's why we end up with 2 hydrogens in there instead. Okay, so it's pretty much the same shortcut. We're just adding different things. Okay, so far questions on reductions. Okay, we're taking pictures of the shortcuts. We're taking another picture of the shortcut. Yes, everything is going to be uploaded probably today, later today, and with the recording as well. Okay. Bless you. Okay, before we do those 2 problems, I'm gonna try to cover the next and final concept for this exam, which is gonna be protecting groups. So we're gonna moving on to the next page. And now, according to what I saw again on the extra credit, he's only gonna test you on a certain group of reagents, yes. In Grignard?
Yes.
There you go. Again, this handout is going to be uploaded entirely so you know what's going to be on the actual exam. Again, remember dog, first exam, cat, second exam. If you see them both, in both exams. Okay, let's go back to this one. Okay, so protecting groups is actually pretty simple, so it shouldn't take us that much time. Okay, so what you have to know about protecting groups is that, really? The purpose of them is so we can preserve or alter the stereochemistry of certain compounds. So let's just start writing that here. So let's just write preserve or alter. Stereochemistry. And also the main part is that whenever you use a protecting group, you're always creating a molecule that has a good leaving group. So let's just add or forms good leaving group. Okay, now there are only going to be 2 main classes. I like to call them just group 1 and group 2. Group 1 is the one that seems like it's going to be on this first exam based on the questions that I saw on the quiz. The second group, I didn't see them at all, but just in case, I'm going to still teach you that today, just in case. Okay, let's start with group 1. And again, protecting groups are only going to be reagents for alcohol groups. We're just going to be working with the alcohols. Now, again, we're just starting with a simple alcohol group in here. And then you can use any of those 4 reagents that you see in there. All of them are protecting groups, and all of them are from group 1. What you have to know about group 1 is the mechanism that it follows. Group 1 is always going to follow an SN2 mechanism. Now, why is that relevant? Because remember, SN2 mechanisms are going to flip the stereochemistry. So notice how we're going from a wedge in here to a dash. That's the main part that you have to notice. If we alter the stereochemistry, that means that we are using something from group 1 because it follows the SN2 mechanism. And you don't have to know the exact full mechanism because it's quite long, honestly. The only thing that you have to know is that you're always going to end up replacing that alcohol group with whatever halogen you have. So that X, that just represents the halogens. So let's say that we had this other reaction with PBr3. Again, first of all, I'm just going to start drawing out that carbon chain. And because I know that PBr3 is from group 1, I'm going to flip the stereochemistry. So now I'm going to draw a dash. And then again, same shortcut. I replace that alcohol for whatever halogen I had. In this case, it's bromine. So pretty simple. It's not that complicated. We always use, well, most of the time we use protecting groups whenever we want to try to do some sort of SN2 reaction afterwards. So we're going to see that later, but for now, just learn those aspects. Again, group 1 follows SN2. And then regarding that, you have to know which one is going to react the fastest with PBr3, for example. In this case, I missed the 3. Is it going to be the more substituted? It's actually going to be the primary one, the less substituted. Remember, SN2 likes something that is not as directly hindered. So the priority is going to be methyl, primary, and secondary. If we have something that's tertiary, that's not going to be able to work because remember, SN2 reactions do not work with as tertiary alcohol, for example. So in this case, remember the priority, it's going to be methyl, then primary, and then secondary. So if we look at those 4 molecules, which one is going to react the fastest with PDR3? A and B? You have to choose. They're both primary? Yes. Just A?
I would say just that.
I would say, why would we not take?
So they are both primary. The difference is that you have to look at the overall steric hindrance. Exactly. So A is going to be the answer. Why? Let's compare A and B. Those carbons in here, those alcohols, are both primary, right? Now, the main difference is that on option B, we follow with a carbon that's tertiary. And it's really close. So there's going to be a lot of steric hindrance, even though that alcohol is primary. On the second one, we have a primary carbon. Then we have another primary carbon. And then that's when we reach the tertiary carbon. So the steric hindrance is further away from the attacking side. So it can proceed faster than B for that reason. So far, questions on protecting groups? Yes. The actual term, I'm not sure if there's an actual term, but I don't remember. There's probably a definition, but from the top of my head, like I cannot remember it right now. And you're not gonna get the question like, what's the name of that position? So I wouldn't worry too much about it. As long as you get the concept behind it, you should be good. Yes.
And SM1, it's the 2-step, and it's the most substitute.
Yes, because of that carbocation that we want to stabilize.
And there's a racemic mixture with it's both in.
Exactly. Okay, let's talk about group 2. Group 2, technically it's the cat. I'm not sure if he's going to include it or not, but just in case. Tosylate and mesylate are your second group of protecting groups. Now, usually he's going to ask a question on how they look like. What you have to know is that tosylate is the one with the ring, and mesylate is the single lady, because she doesn't have a ring in its structure. So that's how I remember it. Mesylate, single lady. Tosylate, she's married.
Wait, what?
Sometimes your professor is going to ask you how tosylate and mesylate look like. The main difference is that one of them has a ring and the other one doesn't. So that's how I remember it. Mesylate, she's your single lady. She doesn't have a ring. Tosylate, she's married. She has a ring. So yeah, there's like fun little mnemonics that you guys should use. Okay, now, yes, there's no ring, exactly. Single lady. Okay, now, main difference that I want you guys to see is that in this case, after we do our protecting, after we use it, we're preserving the stereochemistry. That's the main part that's happening here. Yes. Question? Oh, okay, just making sure. So in this case, let's just write for group 2, we preserve the stereochemistry. And in this case, we're technically following an SN2 mechanism at some point, but remember, the full mechanism for both protecting groups, they're quite long. You're not gonna get asked any questions on that. The only thing that you have to memorize is that for group 1, that's when we actually see that SN2 attack because we flip the stereochemistry. For group 2, we're gonna preserve the stereochemistry. And again, you do not get any questions on the actual mechanism. Now, the shortcut is quite similar. Again, we're just replacing that alcohol group, but in this case, we're actually gonna be replacing only that hydrogen. You're always gonna be crossing out the hydrogen from that alcohol group, and then that's when you add the rest of the protecting group. So in this case, that's why we end up with this whole structure instead of the hydrogen. We're just adding that protecting group. And the main difference is that chlorine is gonna be your leaving groups. Those are gonna be your leaving groups. So they go away and then they're just replaced with that oxygen. And technically, yes, chlorine is gonna be floating around, but we don't really care about that chlorine. Or sometimes you might actually see it as OTS, which represents a tosylate. Or for the mesylate, sometimes we just see it as OMS.
Question, is this still considered a SM2?
I wouldn't think about it, but yeah, at some point in the mechanism, we do follow an SM2
Because
mechanism.
I see the tosylate is flipped. Right?
Tosylate is preserving the stereochemistry. We're going from a wedge oxygen to another wedge oxygen. We're preserving that stereochemistry.
But if you were to flip it, it'll be on a deck. You see what I'm saying?
No.
So you have your ring, so if you look at it right now, right, left to right,
Oh, that group, you can move it around, yes. Remember that that's not gonna be the relevant part. That's gonna be the thing that we're gonna add. And it's always gonna be adding from that sulfur that was connected to the chlorine, because we're basically replacing that chlorine with that oxygen group. So if we flip it the other way, like it's shown in there, it doesn't matter, because at the end, everything in there is planar because of those double bonds. So it doesn't really matter if I flip the molecule one side or the other.
but then that oxygen is still on the way.
Yes, the one that you have to preserve is this one. That one only, the one that formed that alcohol
But
group.
you see what I'm asking, right? Because like you put the molecule.
Yeah,
Right, okay.
okay, so far, questions on protecting groups. We're good? Okay, seems like we're good. Now, I'm gonna stop right there for protecting groups because I'm really not sure if he's gonna cover both groups today. Probably not. So this part is just gonna be for the next exam. So for the next exam, yes, exam
Have
two,
that cost.
yes. So just keep that in mind. Yes. Flips. Mhm. Which one flips is group one? Group two retains.
This isn't gonna be on the exam.
Group one is for sure gonna be in your exam. Group two, I'm not sure about it. I'm just basing it off what I saw in your extra credit exam. The ones that you should probably do because it's very similar and it's really good practice, so please do it.
So group one has the halogen. group
Has
two-
a lot of halogens, yes.
And then group two has
The ring and the lack of the ring, yes. Question? Mm-hmm, yes. Question? Question or? Okay, we're good? Okay. Now, officially, we just covered everything that's gonna be on exam one. So let's go back to Grignard's to finish this part. Okay. It should be pretty simple. Okay, so the very first one, it has, what kind of functional group? What's the name?
ketone.
It's a ketone. Okay, so that's gonna be a very simple reaction. Why? Because we're not doing that double attack. So do you guys wanna use the shortcut for this one and see how it goes? Or do you want to do the full mechanism? Shortcut or mechanism? Let's do the full mechanism, okay. So again, first step, magnesium and bromine, they go away. And that's when I actually have my nucleophile that's active. Grignard's attacks that carbon, that's electrophilic because of that dipole moment. And then I kick up the electrons towards the oxygen to not break that octet. So I have now an O minus, and I added that methyl group that came from the Grignard's reagent. Now, after that, I don't have any leaving groups, so I'm not reforming any double bonds. I'm just gonna end up with that acid-base reaction with the solvent. So at the end, you end up with, you just protonated, exactly. And what's the kind of alcohol that we just created? Primary, secondary, or tertiary? Tertiary, exactly. Okay, yes. If there's a leaving group, exactly. And actually, we're gonna see that again in here because next example and last one is gonna be with an ester. It's gonna be the double attack, exactly. So MJBR goes away and I'm left with my actual nucleophilic species. I attack the carbon, kick up the electrons. And now I have this odd intermediate, O minus, and I'm just gonna write pH, which symbolizes that phenyl group. Okay, after that, again, because I have a leaving group, I reform the double bond, and that's how I kick it out. So now I have a little ketone again. So I have this phenyl group over here. And that alkoxide, which is just my byproduct so far. What's gonna happen now? So pH is gonna come again. Okay. And it's just gonna do the same attack, the nucleophilic attack to that carbon. So again, I end up with a little intermediate that has an O minus. I have the phenyl group from the first attack, the phenyl group from the second attack, and I have, whoops, now it's gonna be protonated actually. With, let's say, with water. I think that was the solvent. Sorry, I'm skipping one step. Right now it's deprotonated. Now at that point, that's when I end up with the water to protonate it. So simple acid-base reaction at the very end. And that's it. I just end up with my alcohol groups. Alcohol, another alcohol. Phenol from the first group. And phenols from the second group. So far, questions on Grignards. We should be pretty good at this point with them. Okay, so we have 6 more minutes. So any last minute questions? Yes. So you can see the difference between Grignards and the other reductions that we did. And that's it. Okay, so very quickly, let's do a quick review. When am I gonna do an acid-base reaction with Grignards?
You don't have an OH present.
When I have an OH present.
Oh, because it's an acid.
Exactly, yes.
It's an acid.
Question? Yes. Because it has a leaving group. And then, what are the rules for multiplicity?
It's for them, right? That's
Which are?
splitting.
That's multiplicity. That's just the definition.
Integration.
No. What are the rules for multiplicity? N plus 1, that's one of them.
Oh,
That's for complex.
I don't know if that-
What about heteroatoms?
They have different J couplings.
Oh, it can't go here.
It can go past heteroatoms. Beautiful. And then what about hydrogens that are part of the same signal? Can they be neighbors of each other? No. Beautiful. And then what does the base peak represent? And what does it actually represent?
The mass,
The most stable fragment, which is going to be for the carbocation. Exactly. Am I always going to see an N plus 2 peak?
negative.
No, it's just going to be when I have which atoms? Bromine, chlorine, and there are 2 more.
Sulfur, oxygen.
And sulfur, oxygen. Beautiful. And that's it. Okay, so for, yes. So yeah. So remember, those ratios only come whenever you're comparing the N plus 2 and the N plus peak. If they're practically the same height, that's like a 1-to-1 ratio, so it's bromine. If it's like a third of the N plus peak, that's when it's chlorine. And then if it's really, really tiny, it can be sulfur or oxygen. Okay, so we're done with the concepts for the actual exam. So on Monday, we're gonna be reviewing. Okay, I'm just gonna go over a little handout that I made yesterday actually, which is basically just summarizing all of the concepts that you should remember and all of the shortcuts. Okay, and on Monday, if you have any specific questions after you do that extra credit quiz, we're gonna do them in here. So if you have any questions on those, just take a quick picture of them and we can do them on Monday. Yes. If you already finished all of Dr. West's and the ones in SI, then sure, yeah, it's good extra practice. But otherwise, no. Okay, any other more questions? Yes. It's gonna be in person during SI. Since we were able to finish everything right now, we're just gonna review on the Monday session. If we have Wi-Fi, yes. So remember, all the sessions are gonna be recorded if we have Wi-Fi. If we don't have it, then I'm just gonna do like a quick summary, like a 5 minutes, and that's it. That's what I'm gonna post. Okay.